Hello everyone, this is the second class of the waves chapter, and now here we are going to study the phenomena of beats. Now beats is actually a pulsating sound. It's a pulsating sound, that is, it grows larger in amplitude for a small time and then goes smaller in amplitude for a small time, just like a heartbeat. So why do we have this phenomena of beats? That's what we are going to study over here. First of all, we are going to see its definition. The definition of beats is as follows. It is a phenomena that occurs due to superposition of two waves with a small difference in their frequency. So like, let's say there is a sound of frequency 500 hertz and there is one more sound of frequency 499 hertz. So you can see the difference between these two sounds, the frequencies, they are different by 1 hertz. So that's a small difference. Now we are going to study the maths first. We are going to see how wave equations allow us to predict such a phenomena, and then we are going to actually hear these beats. So let's get started. So consider that at one point there are two sound waves arriving. Alright, wave number 1, wave number 2. Let's say for the wave 1 the frequency is f1 and for the wave 2 the frequency is f2. For mathematical simplicity, we are going to consider that both the waves have the same amplitude. So in that case, I can write that the equation of the first wave, or equation of the displacement of this particle p due to the first wave. So y1 stands for the equation of displacement of the particle p due to the first wave. So that equation should look something of this form: y is equal to a sine kx minus omega t, wherein I have to put omega 1 over here. But the thing is, because I can choose this point to be the origin, so I can arbitrarily write these equations also as, so although this is correct, but if we want to keep the math simple, we can easily consider this point to be the origin. So in that case, we can write this equation instead as this. Okay, so this is a better form of the same equation. Obviously, I'm not saying that these two are equivalent, but like I've said, if you change the point of reference, if you change your origin, you may well write this equation in this form. So the displacement caused due to the first wave at the point P is now given by y1, which is a sine omega 1t. Obviously you will also put omega 1's value and write this as this. And now, just like we did for the first one, now due to the second wave, the displacement of the particle can be written as this, that is a sine 2 pi f2 into t. So what happens over here is that because both waves are arriving at this point, there will be superposition between them, and that means the net displacement for particle p is y is equal to y1 plus y2. And I'm sure you all realize that when we add these two equations, we're going to have to use a formula of this kind: sine alpha plus sine beta. So obviously I'm sure you do know the right hand side. So what we get here is 2a cos 2 pi into f1 minus f2 t by 2 into sine 2 pi into f1 plus f2 by 2 t. Alright, so this is what we're getting here. It will verify what I've written. Obviously the formula is 2 sine alpha plus beta by 2, so that's 2 sine alpha plus beta by 2 into cos alpha minus beta by 2. Okay, now you might wonder, why am I not cancelling these 2's out. Well, I have a reason for that. I will do it over there, but this one I'm not. So if I write it in this form again, so we have 2a cos 2 pi f1 minus f2 into t by 2 and sine. Now this is where we are going to make a change. See, we have that beats occur when there is a small difference in the frequency. Again, the difference is small. So what happens is that f1 and f2 are nearly equal to each other. f1 and f2 are nearly equal to each other due to the small difference. Now if I use that here, and instead of writing f1 or f2, if I just write f, repeat, I said that because there is a small difference between f1 and f2, so they are nearly equal. So instead of writing either f1 or f2, I'm going to put both of these to be equal to f. So if I do that here, we have got f plus f, 2f, 2f by 2. So we get the same kind of term that we are getting over here. Okay. So this term is common with what we have got here, but the origin of beats lies in these terms. Here there is a simple constant amplitude A, but over here the role of the amplitude is played by this complicated thing, and that is what creates beats. Let's have a look. You see this term, the cosine term over here, has t, that is time, as a part of it. So as time will change, the value of cosine or cos will change, and that is what causes the amplitude to increase and decrease periodically, because cos is periodic, right? So just like when the cos value will increase to 1, you're going to get a large amplitude, but when the cos value will be 0, you're going to get 0 amplitude. So that is how we hear a pulsating sound. Higher amplitude, lower amplitude, higher amplitude, lower amplitude. So that's what we are going to see. Now I'm going to explain what this translates to us, translates for us in hearing. When we are going to hear something like this, some sound which has this kind of equation, what are we actually going to hear? Okay, so what do we expect to hear with this kind of mathematical equation? Have a look at this whole term, that is the amplitude. So I can say that the amplitude of this superposed wave is 2a cos 2 pi f1 minus f2 into t by 2. So that's the amplitude. Now, like I said earlier, that this amplitude is going to vary with cos. So I'm sure you do realize that what this means over here is that this term, okay, if I would highlight this term, if I mark this term has a frequency of this term is equal to f1 minus f2 by 2. Now how do we understand that? Well, again, it's because if you compare with what you get usually inside cos or sine in case of simple harmonic motion, you see it's something like this, cos omega t or sine omega t. So omega is 2 pi f. So if you watch these two carefully, I'm sure you realize that this term has this frequency. Now what this means is that in 1 second this angle is going to make these many periods. I'll repeat, in 1 second this angle and this value is going to make these many periods or these many changes, now these many cycles. So what we have is, we hear a beat, we'll hear a beat or a loud sound only when the amplitude is high. If amplitude A dash is maximum, right? So obviously a low amplitude sound means its intensity is less and we can't hear it easily. A higher amplitude means we can hear it easily. So what this means is we are going to hear a loud sound if the value of A dash is more, maximum. Now I'm sure you all math students would easily realize that here you have a cos term, so the maximum value of cos is plus 1. Okay, let me write that down here. So cos of this thing, right? So cos of 2 pi f1 minus f2 by 2 into t should be 1. But that's not all. There is one thing that is being missed out here, and that one is it's also possible that the value of cos is negative, that is minus pi. So even in that case you are going to get a beat. Even in that case you are going to get a beat, because if the value of this term is negative, what that actually means is here you have something negative, and that simply means that the displacement of the particle is in opposite direction, right? So we're going to hear a beat, we're going to hear a loud sound when the amplitude A dash is maximum, so it could either be plus 1 or minus 1. So be careful about the minus 1, don't miss it up. So now what we have is, if you combine the logic, combine the things that these two sentences indicate, this would mean that in 1 second this value is going to make these many cycles. Okay, but we will hear a loud sound whenever the value is plus 1 or minus 1. Now if you recall what you have studied in your trigonometry lessons, in one cycle the value of cos becomes plus 1 over here and minus 1 over here, right? And every time it becomes plus 1 or minus 1, we hear a beat. So that means when the angle or this term makes one cycle, we are going to hear two beats. One beat for cos value being plus 1, the other beat for cos value being minus 1. So that means how many beats are we going to hear? Well, if this is term frequency, if this is the number of cycles it makes in 1 second, then we are going to hear double the number of beats, because in every one cycle we are getting 2 beats. I'll repeat what I have said very quickly. This term has this frequency f1 minus f2 by 2, that means in 1 second it's making those many cycles. But in each cycle you hear a beat twice because of the values of cos being plus 1 and minus 1, that is twice in one cycle. So that's why we get beat frequency. We get beat frequency is actually double of this term frequency, and that means the number of beats that we will hear in 1 second, number of beats that we'll hear in 1 second is f1 minus f2, which is obviously also called beat frequency. Frequency refers to how many times something happens in unit time. So beat frequency, that is number of beats in 1 second or number of beats in a given time, unit time, is f1 minus f2, where f1 and f2 are the two frequencies involved in the superposition, right? So again, the logic behind this is that we have 2 beats per cycle, okay, and that is why we get beat frequency is f1 minus f2. Now there is a slight catch here. What if f1 is less than f2? All the while we have assumed that f1 is greater than f2, right? Not that this cares, but ultimately you can't have negative number of beats in a second. So what we are going to do is, to be on the safer side, you would always write that beat frequency is equal to modulus of f1 minus f2, in case you don't know which one is greater. So that's the takeaway, that's the key point from this topic. The beat frequency is modulus f1 minus f2. Now, again, the beat is a phenomenon. The beats are a phenomena that occur when you have two sounds of slightly different frequency superposed with each other, and in that case you're going to see a pulsating sound like heartbeats, and the frequency with which you are going to hear the beats is modulus of f1 minus f2. The small difference of frequency. Again, this difference has to be small. Otherwise, our ears cannot sense the variation in sound. So what happens is, when this difference should be about, anywhere between up to, let's say, 8 or 9, humans can hear that. But if you go beyond that, it's difficult to listen to the pulsating sound, and we just feel as if there's a constant sound and there are no beats. So the mathematics is valid, but then here there is a human limitation to what we can hear, right? So that's all about beats. Sound from 500 Hz, so you'll realize what frequency controls. You can see it's not the amplitude, it's not the loudness. Frequency changes the pitch of the sound. So when I decrease it, it's going to sound more like a buffalo rather than a whistle. Again, back up. Now I'm going to show you what's the effect of changing amplitude. As you all would have clearly noted, that changing amplitude changes the loudness. We are now going to produce beats. So for beats, like we have studied, we need two sources of sound. So we need two sources of sound with slightly different frequencies. So let's say that one is 500. I'm going to change it and make it close to 500. Say 502. So now when I'm going to produce both of these, when I'm going to turn both of these on, they're going to produce respective sounds of frequency 502 and 500. And that is what is going to produce 2 beats per second. Remember, 2 beats per second, because the difference of these frequencies is 2. So, alright, let's start. Okay, so I hope you heard it and also counted the number of beats in 1 second. Now we're going to change the frequency from 502 to 503. That will allow us to get more number of beats in 1 second. So let's start. Okay, now why is it necessary that the difference of these two frequencies should be small? Well, the reason is that as the difference gets higher, the beats get faster. That is, the gap between 2 beats decreases and you can no longer hear them separate. So it seems as if there's just one continuous sound and there are no beats. So let's see what happens in such a situation. So you've got this at 500, let's say the other one is at 503, very comfortable to hear the beats. But if I'm going to change this to something like 511, you see the beats are much more rapid. I'm now at 515. So gradually it's going towards being a continuous sound where you cannot hear or you cannot detect the change in the amplitude. Okay, so that's all for this demonstration, and now we're going back to the board. Okay, we are now going to solve example 15.6 from the textbook. I'm going to read the question and note down the details. Two sitar strings A and B, so there are two strings that are going to produce sound A and B. Playing the note the are slightly out of tune and produce beats of frequency 5 Hz. What that means is there is a small difference between their frequencies. It should not be there, but there is. The difference of the frequencies is 5 Hz. But wait a moment. Thing is, we don't know which is bigger. We have to put a modulus. Hope we remember that. The tension of the string B is slightly increased and the beat frequency is found to decrease to 3 Hz. So what we know is that in the case 1, this is what we have earlier. The difference is 5 Hz. Now we are given that we increase the tension in the string. You would have seen that instrument players, they are tightening the strings. Okay, so that is being done. So when we do that, after tightening the strings, the beat frequency remains to be only 3 Hz. That is, the gap, the difference has narrowed. Okay, what is the original frequency of B if frequency of A is 427 Hz? So we are given that frequency of A is 427 Hz. And we have to find out what is the original frequency of B, provided that the new frequency is FB dash, the old one was FB. Okay. Now, the way to go about this problem is, if you start having a look at it over here, we know that FA is 427 and the difference is 5. Now that is only possible if FB is either 427 plus 5 or 427 minus 5. So that means it is either 432 Hz or it is 422 Hz. So these are the two possibilities. It can't be anything else. So let's check the first one. Now think about it. In the second case, it's given that the tension in the string B is increased. So obviously if tension in the string B will increase, that means FB dash is greater than FB, because as tension will increase, the fundamental frequency of a string will also increase. Well, if you could see it over here, tension and the frequency, they are related as follows. The fundamental frequency of a string is F is V by 2L, okay, and V for a string is T by mu under a root. So this ultimately becomes root of T by mu into 1 by 2L. You can see that if tension will increase, the frequency of the string will also increase. Now that would mean FB dash is greater than FB because we are increasing the tension. Now in that case, if it was 432 and FB would increase, the gap of FA and FB cannot be 3. I'm sure you realize that. It's a pretty simple logic. It's bordering on common sense. So again, if it was 422 and this would increase, then the gap will narrow down. You can see, let's say this becomes 424. So the difference would then be 3. Right? So the only possibility is this one and not this one, and hence our conclusion is that FB has to be 422 Hz and not 432 Hz. Alright, so that's it for this simple problem. Okay. Now we are going over to the next topic of this chapter, and the name of that topic is Doppler Effect. Okay, so let's start with it. We're now going to discuss this common phenomena, the Doppler Effect. I'm sure you all have been at the railway station. You would have noticed that when there is a fast moving express train, moving on the tracks. It's crossing you very quickly. The horn that it blows, the sound of the horn, it changes as the train crosses where you're standing. So what happens is when the train comes in, you're hearing a slightly different pitch, different frequency, and then as the train leaves the station, you hear a different kind of sound, different pitch. So what's really happening is that as the train approaches and then as it goes away from you, the frequency of the sound that you are hearing changes. Remember, there's no change with the whistle of the engine. There's absolutely no change. It's still the same. But it's all because of the train coming towards you and the train going away from you that you notice that there's some change. It appears to have been changed. So that's why I'm using the word appears to have been. It's apparent. There's no real change in the frequency of the source of the engine, but still we hear as if it has changed. Okay, so let's see what's the Doppler effect. The definition is the change in frequency of sound, change in frequency of sound as heard or received by an observer due to relative motion between the source and observer. So you can see whenever there is a source and an observer and one of them is moving, you're going to notice Doppler effect. It's also possible with both of them moving, but remember there should be some relative motion between them. Without relative motion, the Doppler effect simply does not occur. Okay, so now that we are done with the definition, I'm going to make you write the formula of the Doppler effect. Okay, the formula first, and then we are going to learn how to derive that formula. Okay. Okay, so here's the formula. Right. So what are these terms? First of all, f dash. F dash is the apparent frequency, or the frequency that is heard or received by the observer of sound, observer or the listener. Okay. F is the frequency emitted by the source. So this is the true frequency, right? And this is the apparent one. So it's possible that the source may be emitting a frequency 400 Hertz, but because let's say the source is moving like the engine, what you receive when you hear it is not 400 and it seems like 403 Hertz. So 403 Hertz is the apparent frequency because that's what you are hearing. But the source was actually not emitting 403, it was emitting 400. So 400 Hertz would be the frequency emitted by the source and 403 Hertz would be the frequency received. So it's the apparent frequency. Now what are these other terms? Well, V vector stands for velocity of sound wave. Obviously we are using this for the sound wave, so it's the velocity of the sound wave, okay, that travels from source to observer. Obviously source is going to emit the sound, that sound wave will travel towards the observer and observer will listen to it. Okay, O for observer, that makes everything easy, so it's the velocity of observer. Okay, and finally there should be no surprises, Vs is velocity of the source that is emitting sound. Okay, so these are the terms. Now, this is a very important formula and it's also very easy to use. Alright, I'm going to showcase how to use it, but before we do that we will derive the formula. Now there are two cases in which we are going to derive, and then we'll combine those cases, we'll get this one. Alright, so I want you to remember this very well. Again, f dash is the frequency that the listener receives. F is the frequency that was emitted by the source, and these are velocities. V vector for velocity of sound, VO vector for velocity of observer, and VS vector, be careful, VS vector for velocity of the source. Now before all that, before we just get on with the derivation, a little thing. You might be wondering, how can we divide vectors? Well, you can't. Okay, you can't, that's a fact. This is mathematically incorrect, but it's still a very convenient way of writing it. Obviously a more correct way would be this. Okay, so this is a way in which you could write it if you don't want to fall into the problem that you're dividing by vectors. But anyways, I like to remember it in this way. It's easy to remember, frankly, so that's all I'm doing now. So let's get on with the derivation. Okay, alright, so let's get started with the derivation. Like I said, there are cases. So case 1, remember that we are going to derive this for case of one-dimensional motion for the source and the observer. That is, you know what I'm saying in a moment. So let's say we're talking about the case where source moves but observer is at rest. Okay, so let's say here is the source S and here is the observer O. Observer is not going to move. Let's say this is the line that joins the source and the observer. Now this was the source position at t equal to 0, but obviously the source is moving, right? So let's say that the source emitted some wave at time t equal to 0. Let's say it emitted a crest. Okay, so let's say it emitted a crest at time t equal to 0 in some time which is equal to time period. Let's say the crest number 1 has reached here. I'm indicating the crest by a line. It could be of any shape. Actually the waves go around spherical form from a point source, but anyways, so let's say that this is where the crest has reached. Let's call this point A. Okay, now obviously I'm sure you realize that this distance should be V into capital T, right? Because the speed of the sound wave is V, capital T is the time period. So in one time period, the wave, the crest, has traveled a distance from S to A, which is equal to speed into time, that's distance, so V into capital T. In the same time, the source won't remain here. Source is also moving. So let's say that the source moves till this point, S dash. So now the source would have moved a distance from here to here. Let's see what that distance should be. Okay, so that distance should be equal to Vs into T. Okay, that distance should be Vs into T. Again, Vs is the velocity of the source. So multiply that by the time it took, so you get this distance, okay, that the source has traveled. So what's happening here is, this is the situation at t equal to 0, alright, and this is the situation at t equal to t. But I hope you remember that the time period of the source is actually the time in which it's going to complete one oscillation, right? And now it will emit the second wave or the second crest. So first crest traveled all the way from here to there in time capital T. In the same time source traveled from S to S dash. Now the source is ready to emit the second crest. Okay, so it's going to emit the second crest from here. So this is the position of second crest. So now what we have is that at time t equal to capital T, crest 1 is over here. At time t equal to capital T, crest 2 is over here. Now these crests are going to travel towards the observer, right, with speed v, the speed of sound, okay, with speed v. So both of these crests, they are going to move towards O. Alright, the source will still move, no problem with that. We are talking about these crests, right? So these crests will move towards O, and that means the distance between these two crests will always remain the same. That's here, right? So basically what we have is S dash is Vst because the source moves with Vs speed. Sa is V into t because the first crest moves with speed v, which is speed of sound. Okay, and so finally the remaining distance S dash a, which is nothing but the distance between two consecutive crests. Distance between two consecutive crests, that's nothing but wavelength, correct? So the wavelength is S dash a, but that S dash a is equal to SS dash SA minus SS dash. So that's VT minus VS. Alright, okay, right, so this is the wavelength, right? Now what we are going to do is we are going to derive the relation of the frequency that is received by the observer. Now what has changed as far as the observer is concerned? The observer is noticing that the wavelength of the wave has changed. Now you see, this is not the true wavelength, right? The true wavelength would be V into t. So what we should call this is actually the apparent wavelength lambda dash. I hope you don't have any problems gaining or understanding what I've said. Again, the crest 1 travels a distance v into t, that is from S to A, right, in one time period, and that is the distance that is called the wavelength, actual wavelength. So that's this lambda Vt. But here the observer is going to get a wave whose wavelength is not Vt, not lambda, but lambda dash, which is Vt minus Vs. Once you understand this, the rest is quite simple. Based on this, if we use the relation that apparent velocity of wave, okay, what should be the apparent velocity of wave? The source is moving, will velocity of the wave change? No, because the velocity of the wave does not depend on source. So the apparent velocity of the wave for observer is still v. It's not v dash, I don't need to use v dash. But now I can't write lambda by t. I hope you realize why. Okay, I'll have to write lambda dash by t dash. The reason why it would be t dash not t, because you see these two crests have come in close. So after one crest is received, the other crest will be received quickly or in a shorter time. So the time period as received by the observer is also going to change. So again, let me clarify that here in writing, where t dash is time period between receiving of two consecutive crests by observer. Okay, now with that done, let's put these values over there. So I can get V is equal to lambda dash. Okay, so I'm just going to write lambda dash's value here. So lambda dash value is V minus Vs, T is common, and then divided by T dash. Okay, so this is what we have now. V is V minus Vs into T upon T dash, where capital T stands for the true time period of the source, and T dash is the time period between the observer receiving two crests. Okay, now I'm sure you do understand, because T is equal to 1 by F, and we should have, by definition, T dash is 1 by F dash. Therefore, this would easily become V is equal to V minus Vs into bracket F dash upon F, and finally F dash is equal to V upon V minus Vs into F. So if you observe what we wrote earlier, the formula that we wrote earlier, F dash is F into V minus Vo upon V minus Vs. I'm not writing the vector sign, I'm sure you can understand it without that as well. What we have here is, you see, we are putting Vo as 0, we are putting that the observer is stationary at rest, and that's why we are not getting this term here. Okay, now we could also do this derivation, right, and we are going to do it by taking the other case where the source is stationary and the observer is moving. Okay, so let's start. So we are now going to talk about the case number 2, where the source is at rest and the observer moves. Okay, so what happens in that case? Well, I'm going to draw another diagram very quickly. This one is simpler in my opinion. So let's say this is SO, and this is where the observer was at time t equal to 0. This is the line that joins the source with observer, and the observer is going to move some distance in some time. That time could actually be, anything. It doesn't have to be, it doesn't really have to be anything special. Okay, so let's say in time t equal to t. Now the basic idea here is that because the source is not moving, right, because the source is not moving, the wavelength is not going to change, right? The wavelength is not going to change. What do I mean by that? See, let's say at some time this source emitted the first crest. Okay, let's say it reached here, but because the source is not moving, the second crest is also going to follow the same kind of time, so with same kind of time. So what happens is, it's just usual, whether the observer moves or not, this has no consequence, this has no effect, and that means the distance between these two crests, let's say 1, 2, 3 and so on, so the distance between two consecutive crests will be lambda. That's different from what we had in the first case, where because the source was moving, the distance between two consecutive crests was not lambda, it was something else, it was lambda dash, which we had to figure out, which we had to find out. Okay, so here we have lambda, right, as the distance between these two. Now I want to talk about the wave velocity. You see, the source is going to emit sound with speed v. Okay, that sound is going towards the observer, but because the observer is moving, let's say towards the right side with the velocity vo, what happens is that for the observer, the wave velocity is actually the relative velocity of the wave. Okay, so it's relative, let me write that in bracket, is going to be v dash, okay, which is going to be v, that is speed of sound or velocity of sound, minus velocity of the observer, because of the basic relative velocity relation that I'm sure you remember. v12 vector is v1 vector minus v2 vector. I'm not writing it on the board over there. Okay, now so this is what we have got, and we know that the wavelength doesn't change. Okay, so that allows us to do the calculation very easily. So again, I'm going to write the basic formula that v dash should be equal to lambda upon t dash. Right. Again, t dash stands for the time period between two crests received by the observer. You see, again, this time period t dash is not going to be capital T. It's not going to be the same as time period of source, because let's say that the observer receives some wave, some crest over here, but by the time the second crest arrives over there, this observer would already have moved. So you can see the gap, the duration between two crests reaching the observer is not going to be capital T. It's going to be more if the observer is going away. It's going to be less if the observer is coming in, coming close to the source, right? Okay, so what that means is it's not capital T, it's T dash, it's something else. But that's not a problem really. We are going to put V dash's value, V minus V0, VO actually, is equal to lambda. Now, we want to get a relation where everything is in form of the velocities. So I am going to write this as V into T. Again, the basic formula that the true wavelength is wave velocity V multiplied by the time period of the source and upon T dash. Now just like we did it earlier, T upon T dash can easily be written as F dash upon F, because as you see over here, time period and frequency are inverse of each other. So finally we have F dash is equal to F into V minus VO upon V. So you can see it once again over here that we are getting the numerator but not getting the denominator as such, because we have assumed that the source remains at rest, which you would easily verify if you put Vs is equal to 0. So that's it for the derivation. You don't need to remember both of these. Like I've said, the one that I started off with works, and it works every time there is one dimensional motion for the source and observer. Alright, okay, so that's all for the theory. As far as the textbook is concerned, there's a few things that I have to tell you for JEE preparations, okay, but we'll do that after we solve a few basic questions from the book. We are now going to solve the example 15.7 from the book. Okay, now this question is in two parts, right? Let's read it first of all. Very important for Doppler effect questions is to draw the diagram, a basic diagram with positive, negative wherever required. It helps a lot, it makes everything very easy. A rocket is moving at a speed of 200 meters per second towards a stationary target. Let's read everything first. While moving, it emits a wave of frequency 1000 Hertz. Some of the sound reaching the target gets reflected back to the rocket as an echo. Okay, so what we have is there's a rocket which is moving towards, which is moving with a speed. So let's say this is the rocket. Okay, remember that's the source S, and it's moving towards a stationary target, right? So let's say this is the observer, which is obviously the target, moving towards the stationary target, going in this direction. So let's say right side is positive and left side is negative. We're going to use all this in the formula. So we are given the following information: speed of the source. Remember, rocket is the source. Okay, calculate the frequency of sound as detected by target. So this is the source, its velocity is 200 meters per second. Again, how do I know it's positive? Because the rocket is moving towards the target, that's towards the right side, which we are considering as positive. These two things are very important. The moment you draw the diagram, you put plus minus, it helps tremendously. Okay, so Vs is this. Now VO, that's the velocity of observer. This observer is a target, it's stationary, not moving, 0. Now velocity of sound, is it given in the question? Okay, we have to take 330 meters per second. So it's positive again. it has to be positive, because the sound will go from the source to the observer this way. So what I recommend is that you also make an arrow for the direction in which the sound will travel. The rocket will produce a sound that goes off to the target, that's towards the right side. So the sound velocity is also positive. And what frequency does the source, that is the rocket, emit? It's emitting a frequency of 1000 hertz or 1 kilohertz. See, you have all the data. Now what you have to find is calculate the frequency of sound as detected by the target. So we use the Doppler Effect formula. The formula is f dash is equal to f into v vector minus v o vector upon v vector minus v s vector. That's it. Put value 1 kilohertz, I'll get the answer in kilohertz. V vector is 330 minus VO, that velocity of the target, 0, observer's velocity 0. So V vector again 330 minus, what's the velocity of this source? 200 meter per second. And we will simplify all this, we get 330 by 130, that is 33 by 13. You will do the rest in a calculator. I don't think you'll have any problem with it. So that's going to be your answer. Okay. Alright, now for part 2 of this problem. This is the rocket over here. Let's say here is the target. So we are going to notice that the sound is emitted by the rocket, hits the target, and then the sound comes back. So the first question is, who's the observer? Obviously this rocket is the observer. Okay. Now the question is, then who is the source? You are going to say this rocket is the source, correct? But if you do it that way, you are going to have to do a calculation twice. Okay, so that's going to be a bit complicated. It's going to be that this is going to emit wave, the sound, this is going to receive it, and then this is going to throw it back. So then finally this is going to be the observer. You are going to have to do it in 2 steps. Okay, step 1, rocket, 2, target, and then again target to rocket. So there will be Doppler effect twice. Okay, you'll have to do all the calculations in 2 steps. But there's fortunately a very simple trick. Look at this. So one thing is quite clear. This rocket is the observer. You can think of it as if you're standing in front of a mirror and you are seeing yourselves. So it's like the light goes off from your body, hits the mirror and comes back to you. So you are the source and you are the observer again. So what we can do here is that we can think of it like a mirror. I'm sure you have studied basics in 10th standard, so it shouldn't be a problem. So this is the observer, this is the mirror. Then where does the sound come from? Well, if you are observing, you could actually see your own image behind the mirror, right? So you could think of it that the sound is actually coming from this source. Remember, this source is imaginary. There's nothing over here behind the target, but the way sound behaves, you could think of it like this. So now what we have is, we can make a list of everything. Okay, we are going to take right side as positive and left side as negative for our calculations. Okay, we have these things to put in the formula, and obviously f, the frequency emitted by the source is 1 kilohertz, as we saw earlier. Velocity of observer, now this observer is going towards the right side, the observer is rocket going towards the right side, so I should write plus or minus? Plus, correct. 200 meter per second, right side positive. Now look at the sound. Okay, so sound will go from left to right or right to left? It is from right to left, because this is going to behave as source, so it's going to emit sound. That sound will travel all the way from here. Remember, what we are doing is we are thinking that if there is a mirror over here, then this is going to make an image over here. So now you don't need this. So sound is going to come directly, you will think of it, sound is going to come directly from the source to this observer, right? Remember, there's nothing over there, it's just a way of handling all of this calculation in one single step. So V is minus 330 meter per second. Again negative because the sound is going to come from the source to the observer. And finally Vs vector is velocity of source. Now see, if this comes close to the mirror, I'm sure you realize that the image also comes close to the mirror. That is, Vs vector is towards the left side and Vo vector is towards the right side, and that's why this was positive, but this one will be negative. Okay, now we have all the data. All we need to do is use the formula, and that's all. Okay, so leaving that part for you. Again, the main thing here is that the proper method would be to do it in 2 steps. From the rocket to the target, the frequency will change because of the Doppler effect, and then again from target to rocket, the frequency is going to change. This is slightly complicated way of doing it, long as well, but this one, the trick, you think as if there is a mirror, and you could do this in all questions where the sound is getting reflected and it's about Doppler effect. Okay, all questions where sound gets reflected and the question is about Doppler effect, right? So think of it as a mirror. Okay, this is the observer because finally the sound arrives here. You can think as if the sound came from the mirror image, and this person over here, anyone over here, is listening to it or detecting it. Alright, I hope you have got this technique clear. Okay, now that we have solved one example, we are now going to solve a question from the exercise. The question number is 20 from the exercise. So, exercise question 15.20. Okay. It says a train standing at the outer signal of a railway station blows a whistle of frequency 400 Hz in still air, that is no wind. What is the frequency of the whistle for a platform observer when the train approaches the platform at a speed of 10 meter per second? So the first part, A. So for A we have one question: what is the frequency heard by the observer? So again I'm going to draw a diagram here. Okay, so this is for 1, right? Here is the train. Train is obviously the source, and let's say here is the station and a man is standing at station, and so this person is the observer. Let's say right side is positive, left side is negative. Now it's given that the train approaches the platform, so that is the train is moving towards the right side. So Vs, train moving towards the right side, positive. How much? 10 meter per second. Okay. What's the observer doing? Well, the observer is stationary. Observer is standing on the platform. Okay, so VO is 0. Okay, because the observer is stationary. Now speed of sound in air is given in the last line of the question. It is 340 meter per second. Alright, so we have all these details, and let's write down what is the frequency of the source. The frequency of the source, that is the train's whistle, is 400 Hz. Now we have to find what is the apparent frequency as the train approaches this platform. So obviously the Doppler effect formula, F dash is equal to F into V vector minus VO vector upon V vector minus Vs vector. Well, we are going to put all the values because we have all of these. So 400 Hz, V vector is 340 minus 0, no need to write it, divided by 340 minus 10, so that is going to be 330. I've just put all the values. Okay, so yeah, I'm sure you can do the rest on your own. So the final answer is going to be some hertz. Alright, don't forget the unit, you must write the units please. Okay, so that's the first part, 1A. Now the question says in 1B, what if the train recedes from the platform? That is, it's going away. What if the train was going away? So instead of Vs vector being right side, the train's velocity is now going to be left side. That is, Vs vector is to the left side. So the only change that I'll have to make for the part B of 1 is that instead of Vs being plus 10 meter per second, I'm just going to have it as minus 10 meter per second, and that's all, right? That's all the change I need to make. The rest just follows the same path. Okay, now the second part of the question, 1a is done, 1b is done. Now it's time for 2. So 2 says, what's the speed of sound in each case? That is, for both of these cases, that is basically in A and B, what's the speed of sound in each case? Again, the speed of sound depends on the medium, not on the source. So whether the train moves or train doesn't move, train's the source, so its velocity does not change the velocity of sound, right? So that's why in both cases, for both cases, you have velocity of sound as 340 meter per second, even as observed by the observer, because the observer is stationary. Remember, instead if observer was moving, the velocity of sound with respect to the observer would be changed, correct? Okay, so keep that in mind. Question 21. Well, there are two parts to this question. Let's read the question carefully. Train standing in station yard. So there is a train that's standing in the yard, blows a whistle of frequency 400 Hertz in still air. So the air wasn't moving. Now the wind starts blowing in the direction from yard to station at a speed of 10 meter per second. So it's best to draw a diagram now. So let's say here's the train, and the train is standing in the yard. Okay, so train is obviously the source, right? Case 1, train standing in the yard. Okay, right, and now wind is blowing, and now here's the observer, right, on the platform or the station. This person's the observer will take right side positive, left side as negative. So let's put all the details. The source is the train is stationary, so Vs vector is 0. Observer, well, not moving, 0. But the speed of sound now is not going to be 340 meter per second only. There's something else going on. It's that as obviously sound will travel from left to right, from source to the observer, but because there is wind from the train to the platform, from the yard to the platform, so because of that wind, the speed of sound will not be the usual 340 meter per second, it will be plus the speed of wind, right? And the speed of wind again is 10 meter per second. So finally what we have is that speed of sound is 350 meter per second. This is obviously as observed by observer. Okay, this is obviously as observed by the observer, don't forget that. Okay, now so the question says, what are the frequency, wavelength and speed of sound for an observer standing on the station's platform? Well, we have answered the speed part. The speed is going to be 350 meter per second. Now we have to find the frequency and the wavelength. For frequency, the idea is very simple. Frequency of the wave depends on, correct, the source. So because it depends on the source, the frequency that is heard by the observer will be same as the frequency of the source, because see, there's no relative motion between the source and observer, though there is wind, but wind doesn't mean there's relative motion. So that's why the frequency will be 400 Hertz. Now once you have found velocity and frequency, I'm sure you can easily find out the wavelength by using the simplest relation, lambda into f dash is going to give you v. So that's all for this part of the question. Now the second, is the situation exactly identical to the case when the air is still and observer runs towards the yard at a speed of 10 meter per second? So they're saying that, okay, we have it this way. If instead of this we would have a slightly different situation where well, here's the train. The observer who is on the platform starts to run towards the left side, towards the train, with a speed of 10 meter per second. Mind well, even in that case, what would happen is that relative velocity of sound with respect to observer would once again be 350 meter per second. The reason being, this one is going at 10 meter per second to the left side, and sound would be traveling towards the right side at speed 340 meter per second. Correct? Obviously there is no wind now, so that's what this second case is about, right? So there is no wind, but this person is running, so that's why the relative velocity would be 350 meter per second. So what happens is, now we have relative motion going on between source, which is stationary, the train stationary, this one is moving, so there is relative motion. So Doppler effect will come into the play, right? So what we have is, if we want to find out the frequency, we have to use the formula, which is, I'm using the formula directly, F into V. Okay, so now you have to be careful here. When we use this formula, F dash is F into V minus VO upon V minus Vs. V is supposed to be the speed of sound with respect to air. It doesn't have to be with respect to observer. We have already considered this is relative velocity 350. So if I want, I can directly write 350 here. Or if you want details, it's actually like this. Sound is moving towards the right side, so positive 340 minus. Now the observer moving towards the left side, so minus 10. So that's how you can think of this 350. Obviously relative velocity V12 is V1 minus V2. Okay, and divided by V minus Vs is simply 340 because the source is not moving. So if you do it like this, you can see you're not getting a frequency that is exactly 400 like here, right? So what has happened is that the velocity of sound with respect to observer has not changed, correct? But the frequency of the sound as heard by this observer has changed, because in the first case there was wind, there was no relative motion. In the second case there was relative motion, so Doppler effect occurs. Okay, and now here also you can find out the wavelength accordingly by using lambda is V by F. So you know V is 350, right? I hope you understand what we are doing. Okay, and that divided by F dash, because the frequency that is heard by the observer is this. So actually you are doing this, the relative velocity upon the frequency heard. So this is going to be 400 into 335 into 34, so whatever this turns out to be. So the wavelengths will turn out to be the same or not same. That's what you have to figure out. Will the wavelength be same? Alright, so that's what I'm leaving for you. And please think why it is same if it is, or why it is not if not. Okay, right? Now that's all I have to give you about the waves chapter. So this is where we are really covered as far as the book is concerned, but there's one more topic that I want to cover. But before we do that, I want you to solve a few questions. So pause this video, see it again if you want, but don't go ahead until you solve the following questions. I'm writing the list on the board. So these are questions from the exercise. Do solve these questions before you proceed. The questions are, okay, wait. So questions are 25, 27. Okay, solve them in this order: 27, 25 and 18. Alright, so these are questions related to Doppler effect and beats. Okay, so that's it for the textbook part. I hope you will finish these problems on your own, okay, and do it well. Good luck.